Now we go into the big daddy, convolutional neural networks, where we're going to work with the CFAR data, the image data set. And at CFAR 100, there's 100 image classes. And again, this data set's available in Keras. So we read it in, and we extract, just like before, the training and test data set, and look at a summary of what we get. And as described in the text, there's 50,000 training observations. These are color images, and they're 32 by 32, but they've got 3 color channels, red, green, and blue. So this is a 4-dimensional array then, this X. And we see the range of any one of these channels is, again, 8-bit. One of them here is 13 to 255. Okay? So the response is a categorical variable. We're going to one-hot encode that to a 100-column binary matrix. So in the digit data, we had a 10-column binary matrix. Here we go to a 100-column binary matrix.
We love that term one-hot, which we learned from our engineering friends, right? In statistics, we used to call it categorical or dummy variables, which is so boring. But one-hot is a great.
You got to love it.
Name.
You got to love it.
So now we're using one-hot from now on.
Yeah, the machine learning community has a genius for picking clever words. Like deep learning itself is a brilliant word. Okay, so we do that, and now we see that the response matrix is 50,000 by 100. Of course, it's very sparse. So let's look at some of the training images using the JPEG package, which is a package for looking at and manipulating images. So we just set up a little framework for doing a little plotting window, 5 by 5. We're going to look at 25 images. We're going to just sample at random 25 of the images and then plot them, and we use plot as raster command. And there we get them. So these images, you know, they're small images, right? They, what was the dimension? 32 by 32 color images. So the resolution's not that great, but they 100 different classes, sort of natural images. There's plants, there's animals, fish, trees, and various things. Yeah. Okay, so now we set up the model, again, using Keras model sequential. And now you see the pipe operator really makes things much clearer here, because there's many layers, and we specify each of the layers separately. Okay. And now we're asking for convolutional, 2-dimensional convolutional filters. And each filter, remember, each filter was a little, like a little 2-dimensional image. In this case, they're going to be 3 by 3 images, little patches that we slide along the target image and do dot products as we're going across. Okay. And the first one, we say what the filters look like, and we tell it what the input shape looks like, which was 32 by 32 by 3. Okay? And then we have a max pooling layer, which reduces each dimension of the filtered image by a factor of 2 in each case. So what that does is it takes each non-overlapping 2 by 2 block and takes the max. Because this filter is trying to find hotspots for certain features that it actually learns in the filter. And then we repeat this. So we take the output of the pooling layer and we apply another filter. And you notice that as the size of these layers, as the size of the images gets smaller, the number of hidden units gets larger. This is all described in the text, so we won't go over it in detail here, but we just run this code. And again, it's just specifying the model. And now we can do a summary, and you can see the details of each of these layers. And we get close to 1 million parameters here.
Wow.
Again, astounding with 50,000 training images. Okay, but if you look here, you'll see there's layers of dropout throughout, and yeah, you know, and so that adds regularization. All right, so at the end we have a dense layer of size 1024. Do we see that? Yes, and then that gets compressed into another dense layer of 512, and finally to the output layer of size 100, because there's 100 images, 100 classes, and that's piped into the soft, you know, that goes through a softmax layer for fit-in. We'll do 10 epochs here, and not even, because this takes quite a bit longer to run, because there's a lot of layers, lots of parameters, and you see the wheel spinning. This progress bar, you can see in gray, it's not even, it's working on the first epoch. And when it's finished, you see one set of dots on the figure. On it goes. We're not going to wait for this guy. So I'll just stop it using that box there. Came up with an error. We don't care. If you've got time, run the whole model and you'll see. It gets an accuracy of about 46%. If you trained it to all the 30 epochs that we intended originally, we'd get 46%. This is not too bad for 100 class data, but if you search the web, currently you'll find that there are instances of CNNs that can get 75% on these data, and it slowly increases all along as people introduce different clever tricks and other bells and whistles.
Which means you might not believe that, we might not believe the 75%, right? Because it's, if they fiddle with the tests.
If they fiddle with the test set, yeah. So, yeah. So there's a lot of, there are a lot of tricks, and yeah, I think that happens, right? You see these competitions, and you see the leaderboard inches up slowly in tiny amounts as people come up with new tricks.
So is that around the state of the art for this data set, 75%?
I believe so, 75%, yeah. So of course, Rob, when you've got, the more images you have, the more classes you have, the harder it is to classify, right? Because the flip a coin classifier on 100 classes only gets 1% correct classification.
So 40 is actually quite good.
So 40 is not bad, yeah. So one nice thing is that some of these deep learning networks have been pre-trained and are available, publicly available, and you can use them. There's a bigger image data set called ImageNet, which has got millions of images and has 1,000 classes for natural images. And it's been trained with a very sophisticated network, and the one we're going to use is called ResNet. And one can actually use it in classifying images. You can actually use it as is out of the box for classifying images, or you can use many of the trained layers as a sort of pre-trained part of your network and just add layers on top of it. So this is really handy. So what we're gonna do is, we've got a collection of images from, of our own, from our photograph album. And we're going to use the pre-trained network to classify these images. So let me just show you the images, which I've got behind the screen here. So here we go. This is an image from a photograph album. So here's an image of a little Lhasa Apso dog. There's a cat. There's a weaver bird. And there's a hawk sitting on a fountain. There's a zoomed in version of the hawk on the fountain. And here's some flamingos. Okay? So there's 6 images. And we're going to see if the pre-trained network can actually classify these images. Okay, so we read in the images. Here's some code to do that. nothing too complicated. We need to turn the images into a form that this pre-trained network can understand. So the pre-trained network's expecting 224 by 224 images. These are high resolution or fairly high resolution images with 3 color channels. And then we turn them into a form that this network can understand. And so there's a few commands here that are needed to do that. So we just run that. So we've got the images in a directory, the same directory we work in, so we can just read in the images. And so now we read in the pre-trained model, which is called ResNet 50. It's a 50-layer convolutional network.
And how many classes does it, or maybe that's not relevant. It's not, are there a number of classes in the pre-trained network? Or
yes, 1,000 classes.
I see.
So this is a data set. The ImageNet data set has 1,000 classes.
And which would have included things like dogs and birds and lots of other things. I see.
Not just your dogs, but species of dogs, and So it's quite a extensive, comprehensive network. So you can see it's read it in. We've done a summary, and the summary goes on and on. In fact, 50 rows describing all the layers. It's really a complex. And this would have been trained on a massive computers, I believe at Google, and taken a long time to train. But we just make use of it. So we've got our X matrix now, which we pre-processed, and then we decode the predictions and we ask for the top 3. So it's going to produce a probability for each of the predictions, and we ask for the top 3 and have it print them out, right? So bingo, it got the flamingo exactly right. The hawk, it called it a kite, but that's not bad. And the other 2 guesses were birds as well. House finch seems a bit of a stretch.
Can we see the picture? Why did it call it a kite?
A kite is a type of bird.
Oh, I see. I thought it was a kite and fly. Okay.
No. But in the picture where we zoomed out, it focused on the fountain rather than the hawk.
I see.
In fact, it didn't see any bird there, and so it classified that as a fountain, right? The Lhasa Apso, it came in second. It said Tibetan Terrier, which looks somewhat similar to the Lhasa Apso is a Tibetan dog species, and so it got mixed up with the Tibetan Terrier, which is pretty good. The cat, to her horror, was classified as an old English sheepdog. Next guess was a Shih Tzu dog, and the third was a doormat. Luckily, the cat can't understand what we're saying. And the final one was the weaver bird, was classified as a jacamar, which does look somewhat similar. Anyway, I think that's somewhat of a success for the pre-trained network.